Okay, so we talked in day one, lesson one, about spontaneity, what that means, and other things about a spontaneous process or a spontaneous reaction. And from your experience, just intuitively, I think that you could probably pick out a couple things that are characteristic of spontaneous processes, particularly chemical reactions. We think of chemical reactions that are spontaneous when, first of all, when they're exothermic. And if you think about like a combustion reaction, yeah, you have to usually kickstart it, like you have to strike the match to get it going. But once you give it that little kickstart, then it's self-sustaining. You don't have to continue to force it to occur. It just continues on naturally. So, from our experience, we observe, we can tell that exothermic reactions like combustion tend to be spontaneous. So if they have a delta H that is a negative value, delta H less than 0 tends to mean that it's going to be a spontaneous chemical reaction. All right. Well, now we know about entropy also. So let's see if we can think of a situation that characterizes entropy and how it relates to spontaneous chemical reactions. Well, it's just the opposite. We learn from the second law of thermodynamics that the change in entropy of the universe for a spontaneous process is positive. And so if the delta S of a reaction is positive, then that's a pretty good indication that the delta S of the universe is also going to be positive. So when the entropy change is greater than 0, that's usually a spontaneous reaction. And why would that happen? Well, what things cause the entropy change to be positive? Well, first of all, if you increase the number of moles, and especially with gases, if you have more products than you do reactants, like if you go from 2 reactants to 3 products, and especially if one of the 3 is a gas, or if you go from like a solid reactant to gaseous products, anything like that, that would tend to be a positive change in entropy, which means it will be most likely spontaneous. And another one of those that shows up commonly is complexity. So if we start off with like pure elements and we react those to get compounds where the chemical bonds are not with the same element, but with some other element, that leads to a more complex situation. And that usually means you're going to have an increase in your entropy from that reaction. Okay, so all that to say that it looks like, from our experience, it seems like, if you think about it, from our experience, that exothermic processes are spontaneous, and also processes or reactions that increase entropy are spontaneous. So there's a problem here. We've got potentially conflicting indicators. So you could conceivably have a reaction that's exothermic, but where the entropy decreases due to this reaction. Okay, so what would be nice is if we had one parameter to kind of combine both of these factors together into one indicator of spontaneity. Okay, well, so far we've already learned one indicator of spontaneity through the second law of thermodynamics. It says that the change in entropy of the universe for a spontaneous process, so the delta S of the universe for a spontaneous process, is positive. Okay, and remember that has 2 parts to it. So the delta S of the universe concerns itself with the delta S of the system, and in our case, because this is chemistry, that system is usually a chemical reaction. So we could also say delta S of the reaction, delta S sub R. But we also have to add into that the delta S to the surroundings. What's going on in the surroundings? That's important for determining spontaneity. All right. So far, this is the indicator of spontaneity that we've learned, but it doesn't have anything directly about the enthalpy change in it. Well, we did learn this relationship between the delta S of the surroundings and the delta H of the system, the reaction, right? So if we just take the negative of the delta H of the reaction and divide it by the temperature, that's the same thing as the delta S of the surroundings. So we're part way there. We've got now this indicator of spontaneity. This will tell us whether the process is spontaneous or not. And it's got both the delta S and the delta H involved. Okay, well, that's okay. But we're just going to clean it up a little bit and redefine something. Oh, but I guess first of all, what we should do is this just confirms what we were talking about up here. Remember that a positive value for the delta S of the universe, so a positive value, the delta S of the universe, means spontaneous. And as we said up here, that usually happens when your delta S of the reaction is positive. So the delta S of the reaction is positive. And it usually happens when the delta H of the reaction is negative, when it's exothermic. So when the delta H of the reaction is negative. And this negative right here comes from the equation above, okay? So if this is negative, and this is negative, we know that negative times negative makes a positive. And so that means that this positive number is only going to get more positive, which means we'll have a positive change in entropy of the universe. Okay, so that's why, this sort of justifies with an equation why this is true. Why, from our experience, we know that these kind of things lead to spontaneous reactions. Well, this equation right here, if you think about the signs of everything, kind of proves that that aspect. All right, so now, like, as I said before, now what we want to do is we kind of clean things up and define a new parameter that just puts both the delta S and the delta H into the same equation. And that parameter is called the Gibbs free energy, and it's symbolized with a G. And so the change in Gibbs free energy would be a delta G. And so what it does is it just combines the enthalpy and the entropy into one parameter to determine spontaneity. And it's derived from that equation that we left off with on the previous slide. So the second law of thermodynamics, delta S of the universe, is equal to the delta S of the reaction plus the negative of the delta H of the reaction divided by temperature. Okay, so what we're going to do is now we're just going to multiply both sides by negative T. Okay, that's the first step we're going to do. If we multiply both sides by negative T, this is what you get. You get negative T delta S of the universe, and that equals negative T delta S of the reaction. And then that temperature term gets canceled out when you multiply it by, and the negative gets canceled out when you multiply it by delta H of the reaction, okay? So that's kind of step one. Now step two is that we're just going to define this term right here on the left of the equal sign as delta G of the reaction, okay? So we're going to define this right here as delta G of the reaction. I mean, it's just a different way of saying the same thing. And we're going to rearrange this a little bit. Okay, and so here is the reaction that is commonly cited as the one-stop shopping indicator for spontaneity. It's called Gibbs free energy equation. Okay, and this is one of those equations you don't need to memorize. It's going to be on your equation sheet, but you do need to know when to use it and how to use it. So that's one of the learning objectives for today, for sure, is to get some practice using this equation right here to calculate a value for the delta G of a reaction, and from that calculation, determine if the reaction is spontaneous or not. Okay, however, there is another way. This is one equation that we can use to calculate the delta G of the reaction, but there is another one, and it should look very familiar because it's just that way of calculating the delta G of a reaction by taking up the delta G's of formation of all the products, adding those together, and then you subtract from that the sum of all the delta G's of formation of the reactants. And so if you may remember from last week, I talked about there's a middle column in that table of thermodynamic parameters, and in that column is what you have these guys, these delta G's of formation. So every element and every compound has in these tables a delta G of formation. And so we could use this equation also to calculate the delta G of formation. It can be done either way, and it really just depends on what information you're given. If you're given a delta H and you're given a delta S, then you use this form of the equation. If you're given a table with lots of delta G, with lots of delta G's of formation in it, or maybe sort of a whittled down table with delta G's of formation in it, then you're going to use this equation right here. Okay, and so that's what we're going to practice for this lesson, using both of these equations to calculate delta G's and also just kind of interpret what the answer means. Once we get an answer, interpreting what it means. All right? So here's what it means. If you, and this is a curveball, so pay attention to this. So if you have a negative delta G, if your delta G is less than 0, that means spontaneous, which is different than what we said for the delta S of the universe. We said a positive delta S of the universe meant spontaneous, but a negative delta G of the reaction means spontaneous. So this is one of those things where it might be a good idea to just make one flashcard to keep it straight, because sometimes it gets a little confusing for students to remember that if the delta G negative means spontaneous, the delta S of the universe delta positive means spontaneous. All right. Okay. So something else about Gibbs free energy is it has meaning. There is some way to interpret that value, because it will be an energy value, like a number of joules or kilojoules, usually kilojoules per mole. And so what does it mean? Well, the name kind of gives it away. Free energy. It's the amount of energy that's free to do work, that's available to do work, okay? So the Gibbs free energy, it represents the amount of energy available to do work, okay? And another important idea, another that you get from the first equation here, okay, is that it depends on the temperature, okay? So right there, temperature is in the equation. So the answer is going to be dependent upon whatever this temperature is. So something that we pointed out again on day one, this lesson one, we said that, hey, some processes are spontaneous only in a certain temperature range. Okay, they're not spontaneous all the time, or they're, you know, never spontaneous, but they could, some things could also be spontaneous within a certain temperature range. All right, so that's another important thing to remember about the Gibbs free energy. Okay, so something I already pointed out to you, that, you know, these delta G's of formation have been collected and put into tables. And so you can use those table values to calculate the delta G of the reaction. And another important thing to remember is we're back to the situation now where pure elements have delta G's of formation of 0. Okay, all these pure elements have delta G's of formation for 0. So that was true for delta H of formation, and it's true for delta G of formation, but it's not true for the standard molar entropies for S. So again, if you look at that, the table on the website, and you find a pure element, any of them, any pure element, you'll see 0 there for delta H, you'll see delta H sub F, and you'll see a 0 there for delta G sub F, but you will see a non-zero value there for the standard molar entropy for the S. And that's because, you know, what's the energy change when I take hydrogen and I make hydrogen? Because that's what this, you know, this represents. This represents the energy change, in this case, the Gibbs free energy change, when I take the element and I make the product, but the product in this case is just the same element, okay? So there's gonna be no energy change. So that's why it's equal to 0 for all the pure elements. All right. Like I said, this is the example problem that I wanted to do using the delta G's of formation that are found in tables to calculate the delta G of a reaction, okay? And of course, you have to have the balanced chemical reaction, which we have right here. And we start with the delta G of the reaction equation that just uses the sum of all the delta G's of formation of the products, and you subtract from that the sum of all the delta G's of formation of your reactants. And again, you just look up these numbers in the table, but the first thing to do is kind of break this out into more specific terms. And so we have two products here. We have the NO2 and we have the H2O. So each of those are going to have their own delta G of formation, which we look those up in the table, and remembering to multiply them times the coefficient, the balancing coefficient that you get from the chemical reaction. Okay, and then with the reactants, remember that the oxygen, its delta G of formation is equal to 0, right? So if you just remember that, it's going to save you a little time, save you a little space. And then for the ammonia, 4 times the delta G of formation of ammonia. So I just look up all those numbers in the table. And again, in a test or something like that, you would most likely be given some sort of condensed table, you know, for you to pick out values from. But just using an appendix in a textbook or whatever, you pick out these values. And of course, with water and some other compounds, it's important to pick the right one. In this case, I want to pick water in the gaseous form, so -2, 28.59. And for ammonia right there, so you just do all that math, and you get a delta G of the reaction of -1101.14 kilojoules per mole. And remember what that, one of the reasons why that's important is because it will tell you whether or not the reaction is spontaneous based on the sign on the delta G. If you have a negative delta G, it's spontaneous. If you have a positive delta G, it's not spontaneous. You know, some reactions are going to be spontaneous all the time, regardless of the temperature. And some reactions are going to be spontaneous, are going to never be spontaneous. No matter what the temperature, they're going to be non-spontaneous. But there are some situations where you have spontaneity within a given temperature range, but spontaneity, but non-spontaneous at other temperatures. So we want to kind of go through that whole range of possibilities. So the first possibility that we're going to talk about is when something is spontaneous at all temperatures, okay? Because the delta G of the reaction is negative all the time, no matter what you do. And so that's in this situation right here, something we already kind of put in our notes, that when you have an exothermic reaction, when the delta H of the reaction is negative, and when you have a reaction that increases entropy, okay, when it's a positive, when the delta S is a positive value, then you're going to have a negative delta G at all temperatures, regardless. Okay, and that, again, it flows from this equation for the Gibbs free energy change. So we're looking for a negative value on delta G. Okay, well, if I have a negative delta H, that's what I said right here. The delta H of the reaction is negative. So if that is negative, and I have a positive delta S, so that is positive, and I have this negative coming from the equation itself, and a negative times a positive is a negative, right? Negative times a positive is a negative. So I'm going to take this number that's negative, and I'm going to subtract something from it. So it's only going to be negative. There's no way I can change this. You know, I can overwhelm this and turn it into a positive number. So this delta G is always going to be negative. So therefore, it's always going to be spontaneous. So when this is true, when you have an exothermic reaction, that reaction also has a positive delta S, then that reaction is going to be spontaneous at all temperatures, no matter what. Okay. All right. So now we're going to look at the mixed bag, so to speak. Sometimes it's spontaneous, sometimes it's not. So that occurs, first of all, if you have an endothermic reaction. So if your delta H of the reaction is positive, it's greater than 0, but your entropy change for the reaction is also positive, okay? And you're at high temperatures. That's when your delta G for the reaction is going to be negative. So that's when your reaction is going to be spontaneous. And once again, I apologize. I mentioned this last time. I'm still finding instances where this subscript R is on the wrong place, because in the previous textbook that I taught from, that's the way they did the annotation, but I'm still finding them. Okay, so going back to this equation right here. So, and we're going to put these two values into this equation. So we said the delta H was positive and the delta S was positive. So there you go. So if the delta H is positive and the delta S is positive, okay, and this negative comes from the equation, well, look right here. So at a high temperature, this is going to be a really big number. And so overall, this product is going to be a big negative number. Negative times a positive is a negative. So if my temperature is high, then this is going to be a large negative number, perhaps big enough to overwhelm this positive number, which would result in a negative delta G, which means spontaneous. But then we have the situation of a low temperature. So it's still a negative value, right? Negative times positive is negative. But because it's that's a small number, this T is a small number, it's probably not big enough to whittle down this positive all the way to 0 and convert it into a negative outcome. So you're probably still going to end up with a positive delta G. Because this is a low temperature, then this is a negative number. It will subtract from this positive number, but it's probably not big enough to subtract away all of it, and therefore you end up with a positive delta G, so a non-spontaneous process. So when you have an endothermic reaction that does increase entropy, it will be spontaneous at high temperatures only. Now you might be saying, well, what's a high temperature? Is it 100 degrees or is it 500 degrees? Well, what is it? Well, it does depend on each reaction. It is relative. And so we're going to actually talk about how to use calculations to figure out what that temperature is, where that transition occurs, but not yet. We'll get to that part. Okay? All right, so that's one scenario where the temperature dependence shows up. Here's another. So let's say that now we have an exothermic reaction, but the reaction decreases the entropy of the system, okay? So negative delta H and then negative delta S. This is where it's spontaneous at low temperatures, okay? So that's where your delta G becomes negative at low temperatures. So here's why. Okay, so once again, we start with this equation. The delta G equals delta H minus T delta S. So now we're gonna put in these conditions right here. So then the delta H is negative, and the delta S is negative. Okay, so we got a negative delta H, and we got a negative delta S. But remember, this equation also has a negative in it. And this negative gets multiplied by this negative, making it a positive. So now this overall is a positive term that's going to kind of diminish the magnitude of this negative number. It's like we're going to be adding something. This becomes positive, so we're going to be adding something to this negative number. And so if we only have a low temperature, if this is a small number, then we're not going to overwhelm this negative number. And so our delta G will still be negative. It will be spontaneous at low temperatures. But if this temperature is high, if it's a large temperature, then this becomes a large positive number. Negative times negative is a positive, and now it's a large positive number, which could overwhelm this negative number to give us a positive outcome, which means non-spontaneous. So this is a scenario where you have spontaneous reaction when your temperature is low, and you have a non-spontaneous reaction when your temperature is high. Okay? All right, so one more scenario to talk about. So, oh, actually we don't. So, you know, the point here, I guess, that I'm trying to make is that there's two things you have to consider. You've got that enthalpy term, and you've got that temperature times the entropy, the change in entropy term, okay? And so it depends on each of them, and they may be sort of counteracting each other. So that's why, you know, it's kind of like a tug of war. And the larger one, the larger term, is the term that will determine whether or not the process is spontaneous. So, you know, that's what this animation is kind of meant to illustrate, that it's like a tug of war. And so if this is your delta H term and this is your delta S term, then, you know, whichever one is larger, your T delta S term, you can, not just the delta S, but it's T delta S. So whichever term is larger, that's gonna win the war, so to speak. Okay. All right, so if the magnitude of delta H is larger than the magnitude of T delta S, then the enthalpy term wins. If the T delta S term is larger than the delta H term, then the entropy term wins. And that will determine whether or not the process is spontaneous, the reaction is spontaneous. Okay, so now if you prefer to memorize things, if you don't like going through the logic of it, you just prefer to memorize things, then this table is for you. So you can, you know, print off this slide and just memorize this information, or you can make 4 different flashcards, or however you want to do it. But this shows you the conditions based on delta H and delta S and whether or not it's spontaneous or not. So as we said, if we have exothermic, so a negative delta H and a positive delta S, then that's always going to be spontaneous, okay? But if we have an endothermic reaction, delta H is positive, and we increase the entropy due to the reaction, then it's going to be spontaneous at high temperatures. And then, you know, exothermic, but a decrease in entropy, spontaneous at low temperatures. And the scenario that we didn't go over explicitly, but, you know, you can kind of understand it by process of elimination. You know, if you have an endothermic reaction that also decreases the entropy, then no matter what, you're going to have a non-spontaneous reaction. It doesn't mean that the reaction can't occur. It just means that it's never going to be spontaneous. You will always have to force that reaction to occur, okay? So, like I said, you can either think it through logically with that delta G equals delta H minus T delta S equation, or you can, you know, memorize these possibilities right here. Whichever way, doesn't matter to me, okay? So remember, we had a couple scenarios where the reaction or the process was only spontaneous in a certain temperature range. And so we can use an equation that we learned to calculate at what temperature that transition occurs. So at what temperature will a reaction that is non-spontaneous become spontaneous, okay? And that is when that delta G transitions or changes from a positive value to a negative value, okay? So how do we figure that out? How do we get an equation to calculate that temperature? Well, we start with this equation, okay? So we know that delta G is equal to delta H minus T delta S, okay? And so in order for something to transition from being positive to negative, or from negative to positive, it has to go through 0. So we set that equal to 0. And what I'm going to do is I'm just going to rearrange and solve for the temperature. Okay, so we rearrange this equation, solve for temperature, and ta-da, you get this equation right here. The temperature at which the reaction or the process transitions from being spontaneous to non-spontaneous, or vice versa, is just the delta H of the reaction divided by the delta S of the reaction. Okay, so here's an example. So this is actually a reaction that is used to produce iron from iron ore. So this formula is the chemical formula of magnetite, which is an ore that comes out of the ground. And what you do, or what the smelting industry does, is they just heat it up with some charcoal, some carbon, just pure carbon. And what you get out of it is pure iron, right? And then some product gas, carbon dioxide, you get that out of it. Okay, so as we said in the previous slide, what we need to do is we need to divide the delta H of this reaction by the delta S of this reaction. So many times these numbers will just be given to you, right? In the problem statement, they could just give you the delta H and the delta S. I'm pretty sure you have a homework problem where it's like that. But if they did not, then you could still go to the tables, and using this chemical reaction, you can figure out what the delta H of the reaction is by just looking up all the delta H's of formation for each of these participants in the reaction. And the same thing for the delta S of the reaction. If it's not given to you, then you could use the equation that we've learned to just do the same thing. Just look up all your standard molar entropies of the products, you add them up, subtract from that the sum of all the standard molar entropies of the reactants to get that delta S value. So then it's a very simple calculation. You just divide the delta H by the delta S, okay? But the other thing you need to remember, here's the curveball, and this is part of the reason why I said that, typically typically entropies are in joules, and typically enthalpies and Gibbs free energies are in kilojoules. So in this case, we've got kilojoules versus joules. So we've got to reconcile that. And the way you can do that is you can convert the kilojoules here for the delta H into joules with, 1,000 to 1. And so if you do the math, you just get a value of 835.1 Kelvin, okay? So this is the temperature at which this reaction becomes spontaneous, okay? So that's how you could calculate it. All right, so, and the other thing about it is, remember that we did pull these numbers from tables, and those tables were specific to the temperature being 298, but it is safe to assume that those numbers won't really change much with the temperature. And the reason why just kind of gets beyond the scope of this course. So you'd have to take, upper level chemistry class to really get more in depth into that. But for now, that just understand that even though these table values that we use to calculate these two numbers, these table values specified 298 Kelvin, they're still good to use in this equation right here. Okay, so in this question, we have carbon, and we're reacting with water to produce carbon monoxide and hydrogen gas, okay? And by the way, this is one way in which they produce hydrogen. So hydrogen that's used for a lot of different applications out there in industry, this is how they produce it. They'll just take charcoal and they'll react it with steam, and it generates carbon monoxide. But the most important thing is that it generates that hydrogen, which can be used. Okay, so the big thing is that is not a spontaneous reaction at room temperature. And so the question is, at what temperature does it become spontaneous? And so the strategy here is you need to, use your table values to calculate a delta H of the reaction and calculate a delta S of the reaction. And then once you do that, you just divide the delta H by the delta S, and you'll get the temperature, okay? So the temperature is just the delta H divided by the delta S. Okay, so if you do the delta H of this reaction, it's just the delta H's of formation of the products minus the sum of the delta H's of formation of the reactants. So you can separate that out into the different participants in the reaction. Go to your table, look up those delta H's of formation, and you plug those in. And again, in this case, we have pure elements like carbon and hydrogen. So they're going to be 0, 0, and 0. 0 for the carbon, 0 for the hydrogen. And you get 131.305 kilojoules per mole. And then you do the same thing for the delta S of the reaction. And, you look up those numbers, and it comes out to be 133.9 joules per mole Kelvin. And so then you just divide the delta H, remembering to convert it to joules so that things cancel, divide it by the delta S, and you get 980.4 Kelvin. Okay, so it's at that temperature that this reaction becomes spontaneous.